So 13th chapter, magnetic effects of electric current, 10th class physics. So we'll see few topics. So first of all, what is meant by magnet? Because this is a chapter you see. In last chapter, electricity, we have seen one concept, that is heating effects of electric current. So what is meant by heating effects of electric current means, so this electric current will be acting as an input. By using this electric current, and if you can send electric current few certain devices like iron box, toaster, bread toaster, water heater, something like that, and we can produce heating effect. So heating effect is an output. Same concept will be applying here. You see magnetic effects of electric current. Magnetic effects of electric current means magnetic effects, magnetism can be produced by using electric current. So electric current will be acting as an input. By taking that electric current, by sending that electric current to certain devices and certain conductors, we can produce magnetic effect. So magnetic effect will be as an output. That is a very simple concept of this chapter. And you see this chapter is divided into two phases. So first one, in first phase, what we learn is we can produce magnetic effect by using electricity. So magnetism, magnetic field, magnetic effect can be produced by using electricity. In second phase, in second part of the chapter, we learn electricity can be generated by using magnetism. So magnetism, magnetic field can be produced by using current. In second concept, second half, we'll discuss electricity can be produced by using magnetic effect. So here this concept, actually this concept is deleted for this academic year, which is nothing but working of electric generator. If time permits, we'll discuss that also. So we'll see working of motor and working of generator, everything. So first let us go with a few basic concepts. Magnet. First of all, what is meant by magnet? Magnet, a piece of iron or other material in the sense it will be like an alloy which has its component atoms so ordered that the material exhibit properties of magnetism and align itself in an external magnetic field. Okay, we don't want all these big definition sentences. Magnet is a piece of iron or it is a piece of an alloy. So what is alloy? Alloy, we know it is a combination or mixture of two or more metals or non-metals also. Here we'll be taking one alloy known as alnico. Alnico, nothing but it is a combination of aluminum, nickel, and cobalt. These are magnetic materials. Now, by combining all these three metals, aluminum, nickel, cobalt, we'll get one new alloy that is known as alnico. And if that is magnetized, automatically that iron piece or that alloy becomes permanent magnet or hard magnet, where it can hold that magnetic property for long time, long duration, maybe months, maybe years also. And they will be using some other alloys like carbon steel, iron steel, cobalt steel, like that alloys also they will be using. So maximum in your laboratories, what magnets you are observing, they are alloys, and which will be attracting magnetic materials, which can show magnetic properties like attraction, repulsion, etc. Now, properties of magnet. Magnet has few properties. Number one, attracts material like iron, nickel, cobalt. So that magnet will be attracting magnetic materials. So iron will be attracted by magnet, nickel will be attracted by magnet, cobalt will be attracted by magnet. Second property, attraction is maximum at poles. Why? That we'll discuss. Why attraction will be maximum at poles? By observing this diagram, we'll discuss. And attraction will be very minimum at the center of the magnet. That also you have to understand. So this point, attraction is maximum at poles, north and south. Magnet has two poles, north pole and south pole. Why not east and west? Because if you take that magnet, if you tie that magnet with a thread and if you hang it, that will oscillate for some time and it comes to rest at one position. What is that position? Means always magnet will be pointing towards north and south. And don't utter like what is the direction, which direction magnet shows. Means you should not say magnet always shows north. No, it shows north and south, both. Okay, so it will be coming rest to north and south, so that magnet has north and south poles. It will not come to east and west direction, so that there is no east and west poles for the magnet. Next point, always align itself in north-south direction. Don't tell only north, don't tell only south. It is north-south direction it will come. And a few other properties like poles, which they didn't mention, but in 6th class we have learned. Like poles always repel, and unlike poles it will attract. So these are the few properties of magnet and magnetic field. So what is that new word, magnetic field? It is simple, space around a magnet where its influence can be experienced by other magnet. Means if you take a magnet, for example, if you take a magnet like this magnet will show its influence to certain level, to certain area, to certain space. Let us consider this is the area where this magnet will be showing its influence, and this area or the space or the region around the magnet is known as magnetic field. Earth has gravitational field now. For example, this is Earth. Let us consider Earth has gravitational field until here. Let us consider. Means what? If you throw any object, if it is reaching to this height, it falls down. If it reaches to this height, it falls down. If it reaches to this height, it falls down. But if you keep an object here, which is not in the gravitational field, if you keep it there, what happens? That will be remaining in space only, like satellites. We'll be sending satellites to the space. So while we are sending satellite, we'll drop satellite at certain level. Why? This satellite should not be in the influence of Earth's gravitational field. Earth should not show any influence on the satellite, so that that satellite will be revolving around the Earth in certain orbit. Same like that. Magnet has space around it where it can show its influence, and it can attract or it can repel. For example, let us consider this is North Pole, this is South Pole. If you place a magnet like this, which is North Pole here and South Pole here, we have seen property same, like poles will repel. So north, what happens? Definitely it will repel, and that magnet might turn like that. It might deflect like that, right? Or if you place any compass needle here, yeah, it can show, this magnet will show influence on this compass needle. But if you place compass needle here, this magnet cannot show its influence on that compass needle, because that compass needle out of the range, out of magnetic field. So area or the region or the space around magnet where this magnet can show its influence, either attraction or repulsion it can show, that is known as magnetic field. Simply to say, field around magnet is known as magnetic field. And magnetic field lines, they are curved imaginary lines. You cannot see those lines. No, with the naked eye, that magnetic field is not visible. Magnetic lines are not visible. You see, can we see gravitation? No, we can feel gravitation. We cannot see gravitation field or something. We can feel it. Just if you throw any object up, it falls down. If you jump, you will fall down. That is the observation what we can do. So magnetic field lines are curved imaginary, that is most important. Imaginary lines used to show magnetic field in a given region. For example, this is the magnet what we have with the south and north pole, and there are few lines. What are those few lines? Those lines are magnetic field lines. And there are few properties for magnetic field lines that also we are going to discuss. So magnetic field lines, it is closed imaginary lines, and those lines will have few properties. Number one, magnetic fields are closed continuous curves. So they are closed. So there is no starting point, no ending point, something like that. It is closed and it is continuous. Always that magnetic field lines are continuously, it will be in motion. And curves directed from north pole to south pole outside. Means if you take bar magnet, you see this is north pole and this is south pole. Always magnetic field lines will be starting from north and it will be moving. You can see the direction like this. It moves towards south, that is outside. Inside what happens means that will be moving from south to north again, like this. And again it will be moving from north to south outside, south to north inside. It is closed. You see, it is completely closed. It may not be like a circle, but it is like an ellipse now, elliptical. So it is closed and continuously it will be in motion, and it has direction. Outside it is from north to south, but from south to north pole inside the bar magnet. You can observe that. So like that you can draw another line from north to south. Again you can close it, you can close that and draw an arrow mark. So like that magnetic field lines can be drawn around magnet like this. So arrow marks you have to draw, and you see here again from north it is starting, it is moving like this. Moving like this means don't consider that line is ending here. No, if you draw, if you extend this line, if you can extend this line, it might reach here. You can see it is closed, big one. It is a big ellipse, big closed curve, that one. And you see this one. You see this line? It is moving like this. And after that, where it will reach? It will reach here. So, like that. It is closed continuous curve. Because of the space what we are doing, we cannot draw all the curves, and we cannot draw big lines, big curves we cannot draw. We cannot mention more number of circles, so that we'll make it simple. And you see middle, the line, it should be straight, which will be moving from south to north. Line should be straight. Mention arrow marks like this. And here down, yeah, it is from north to south only. Directions are important. So that is first property of magnetic field line. Next one. Tangent at any point on the magnetic field line gives the direction of magnetic field at the point. Means if you take any compass needle, let us guess. If you take compass needle, and we know compass needle which will be round and which has some magnetic needle inside it, which will have some arrow mark. That arrow mark always it will point towards north, and this down part always it will show south. So always it will be directing towards north and south. And if you place that compass needle here, that compass needle also will show the direction like this. If you place compass needle here, it shows this direction. If you place compass needle here, it shows this direction. You see, if you place compass needle here, it shows this direction. And if you place it here, it shows this direction. So you are getting, I think so, like this. So that is the direction. Compass needle will show direction of the magnetic field. Next point, magnetic fields are closer together at the poles and far apart at the center. If you observe, near poles, magnetic field lines are very close to each other, like this, right? Very close. So that degree of closeness represents strength. Near poles only we can able to see many magnetic lines. You see many magnetic lines we can observe near poles. So that only here we have studied one concept. Attraction is maximum at its pole. Why? Because that crowded lines, the density, magnetic flux density, that represents strength. And if you observe in the middle, we don't have any lines in the middle. Nothing is there in the middle. So that attraction will be least at the middle. Then magnetic field lines never intersect each other, as its magnetic field cannot have two directions at one point. Means if you see, there will be only one east, one west, one north, one south. Just if you look like this, and if you say this is east, east and north cannot be present at the same place now. If this is east, that must be west, and this must be something north, and this must be south. So you cannot get east west or east south or east north at the same point. No, it is not possible. Means here what it is trying to tell me, consider we have two magnetic field lines like this. Consider this is one magnet. North pole is there here, south is there here, and we know magnetic lines of forces will be moving from north to south. It is moving like that. Let us consider. And let us consider we have another bar magnet. Here we have another bar magnet which has north pole here and south pole here. Let us consider. Okay, now from here we are getting another magnetic field line which is moving like this. Basically, this intersection is not possible. It is not at all possible. Two magnetic field lines never intersects. Never. Why? Okay, if I take compass needle and if you place compass needle here, it shows which direction? This direction it will show. Okay, if I place compass needle here, which direction it will show? It will be showing this direction. Okay, now if I place compass needle here, which direction it has to show? Will it show like this or like this? No, at the same time it cannot oscillate. Na? It cannot oscillate. If it is oscillating, then what is the meaning? Means north is this side and north is this side. Is it possible of getting north pole two sides, two directions? No, it is not possible. Not at all possible. So that magnetic field lines never intersect. That is the point you have to understand. Then next concept, magnetic field due to straight current carrying conductor. The magnetic field due to a straight current carrying conductor. Now what we are doing in the sense, we are entering into the concept of relationship between electricity and magnetism. So till now we have seen only magnet, what magnet is and how many poles magnet has, what about the attraction, what about the repulsion, what about magnetic field around inside and outside the magnet, that and all we have seen. Now let us try to introduce the concept of electricity in magnetism. The magnetic field due to a straight conductor carrying current, you see, in conductor, if you pass current, it becomes current carrying conductor. Try to understand the word. Whenever I utter current carrying conductor, we have to assume that, okay, there is one conductor and electricity is passing, current is passing in the conductor. It is in the form of concentric magnetic lines of force. So what is that concentric? It is concentric circles whose center lies on the conductor. These magnetic lines of force lie in a plane perpendicular to the plane of linear conductor. Means if you have current carrying conductor, for example, let me draw it here. Okay, consider we have straight current carrying conductor like this, where current is passing, maybe in this direction, I, current is passing. When current is passing through straight current carrying conductor, definitely magnetic field is produced around conductor. And how that magnetic field will be there means, magnetic field will be in form of concentric circles, means like this, and that will be continuously in motion, na? So that will be in form of concentric circles, and that circle will be very small, the diameter, or you can call it as radius, or you can call it as circumference or diameter, whatever it may be, that will be very small near the conductor. As you are moving forward, that a circle circumference will increase. So from that, what we can get information is, near conductor, very near to the conductor, there will be greater magnetic field. And as you are moving away, from the conductor, that circle diameter or circumference or radius is increasing, where there will be decreasing in the magnetic field strength. Very near to the conductor means at this point, maybe at this point, there will be greater magnetic field. At this point, there will be less magnetic field, weak, it will be weak. You cannot observe deflection also sometimes. If you keep compass needle here, for example, here if you place compass needle, yes, you might observe some deflection. But if you place compass needle here, you see how much distance is there from conductor to compass needle? More, na? You cannot observe that much deflection. That deflection angle decreases. So, and what they have said, these magnetic lines of forces lie in plane perpendicular to the plane of linear conductor. You see, this is linear conductor, straight line, and magnetic field, how it will be? It will be perpendicular like this. So you can draw arrow marks here. So it will be perpendicular. Next. Now, strength of magnetic field produced by straight current carrying conductor wire at a given point is, you see 2 points we have to understand. There is some current carrying conductor. I mean, there is one conductor. We are passing current through conductor. Now that conductor has become current carrying conductor. What about the strength? What about the strength of magnetic field produced by that current carrying conductor? Means 2 points we have to remember. Number one, that is magnetic field strength, which is mentioned with capital B, that is magnetic field. In 12th class, you will learn. B is a representation of magnetic field. That magnetic field is directly proportional to the current passing through it. I means if you increase value of current, magnetic field also can be increased. Strength of the magnetic field also can be increased. If you decrease amount of current in the conductor, if you decrease strength of the current in the conductor, automatically strength of magnetic field also will decrease. So both are directly proportional to each other. If you increase current, magnetic field can be increased, strength of magnetic field can be increased. And second point, inversely proportional to the distance of that point, means magnetic field can be decreased by increasing the distance. So B is inversely proportional to distance R. B inversely proportional to R, means if R distance is increased, magnetic strength will be decreased. That's what I told you here. If you see this one, compass needle, if I place compass needle, yeah, we can observe some deflection. But if you place compass needle here, you see the distance. When distance is increased, magnetic field will be decreased. Here also same concept I said. When you are moving away from the conductor, that circumference or diameter or radius will increase. When it is increasing, magnetic field decreases. So those are the 2 points you have to understand, and they are important because they might ask questions regarding that one also. So B stands for magnetic field, I stands for current, R stands for distance between wire and point of observation. So this can be written as, I mean, both can be combined. Which one? B directly proportional to I. Magnetic field, strength of magnetic field is directly proportional to current. Strength of magnetic field is inversely proportional to distance. Both if you combine, it becomes like B directly proportional to I in the numerator upon R in the denominator. So when it is in numerator, it is directly proportional. When it is in denominator, it is inversely proportional. Magnetic field strength directly proportional to current, magnetic field strength inversely proportional to distance. Now SI unit of magnetic field. For magnetic field, there is one SI unit, that is Tesla. That is a scientist name, so that capital T name will be in small letters. And what is 1 Tesla? 1 Newton upon 1 ampere 1 meter, means 1 Newton of force is applied for the deflection. That we'll discuss. Newton is SI unit for force, na? Why that force we got? In next lecture we'll see. 1 ampere of current is produced and 1 meter of distance. And of course, this is not there in your 10th class textbook, so no need to remember that SI unit of magnetic field strength. But anyhow, we have discussed, you can remember that. And you don't want all these Gauss, field of Gauss, Tesla, no need, leave this. Moving to next concept, that is right hand thumb rule, which represents direction of current and direction of magnetic field. What is that right hand thumb rule? The straight thumb of right hand means you have to take your hand, right hand, and you need to close all your fingers except this thumb. Except this thumb, all fingers must be closed. And by closing this one, this gives some information about relationship between current and magnetic field. What is that relationship between current and magnetic field? Means, you see that thumb indicates direction of electric current passing in conductor. Passing in conductor. The direction of curl of fingers. We have closed all fingers, na, this one. We have closed all the fingers. So these fingers, 4 fingers, which will be showing, that will be representing direction of magnetic field around conductor. So direction of current in conductor represented by thumb. Means if you are holding like this, consider one imaginary conductor. For example, here only we have one conductor. Let us guess. We have conductor, and this conductor, if a current is passing in this direction, you will be holding conductor like this. So this thumb is indicating what? Direction of current, means current is passing in this direction like this. And wrinkled fingers. This wrinkled fingers showing direction of magnetic field around conductor. You see that imaginary diagram where we can observe that one, where this is a straight current carrying conductor, where this guy is holding with the right hand, and this thumb is indicating direction of current in the wire. And you see he is holding like this now, he has closed. So you can observe the direction of finger and nails, fingernail, it is pointing that side. So magnetic field will be like this around the conductor. So if conductor is like this, if current is passing like this, you will hold fingers like this na. So that is the direction of magnetic field. Consider this is the conductor where current is passing like that. If current is passing like that, you will be holding like this, right? So your thumb will be here and fingers will be closing like this na. So if current is passing in this direction, magnetic field will be in this direction. If current is in this direction, magnetic field will be in this direction. So from this, what we can infer means only one point we have to understand. There is direction for current. Whenever current is passed through conductor, you can get magnetic field. Magnetic field. For this magnetic field also, there is direction. So there is direction for magnetic field. Now, one small concept. If you try to change the direction of current, obviously we can observe change in direction in magnetic field. You see, when current is passing like this, you will be holding conductor like this. Like this you will hold. Na? So that magnetic field will be considered like this. If current is passing in this direction, magnetic field might be in this direction. So when there is change in current, there is change in magnetic field. Most important point you have to understand and remember. Then let us try to see another concept, that is magnetic field due to circular coil. So now we have seen straight conductor. So just a straight wire, if you are passing current through this straight wire, we know magnetic field is produced. That magnetic field will be in circular shape. And this current has direction. This magnetic field also has direction. If you change direction of current, there will be change in direction of magnetic field. That point we have discussed. Now let us discuss magnetic field due to a circular coil. Means take one conductor and make it like a circle. You see, take this conductor and hold here and here. Try to bend this. If you bend, what happens? It becomes round. Now for this conductor, if you pass electricity, of course we know when electricity is passed, when current is passed through the conductor, obviously magnetic field is produced. When if the conductor is in straight, we have observed that magnetic field will be in a concentric circle. Now if electricity is passed through circular coil, then what about the magnetic field? You see, the magnetic field lines are nearly circular and concentric. Yeah, they are circular and concentric. Let us consider this is the point. If you consider this point, yes, we can observe circles. Circles you can observe. And I told you another concept, that whenever you are moving away from the conductor, here I think so, here I said, when you are moving away from the conductor, when distance is increased, what happens? Automatically, that circumference of the circle, diameter of the circle, it will increase, isn't it? It will expand, it will increase. Same like that. We have chosen one point. Na? This is the point we have chosen. Where this one. So near conductor, that magnetic field will be circular shape. If you are moving away, what is happening? That circle is increasing. Actually means this one. It is not the end like this circle. This is not the end, guys. Circles. So circumference of the circle increasing. So that what happens? That circumference will increase, further increases, And at last, exactly in the middle, you see, this is also not a line. This is a circle. You have to draw a big circle like that, like this. So exactly while coming to the middle of the conductor, center point of the conductor, that magnetic field will be in exactly straight line, straight line. And again, if you are moving down, if you are moving again towards the conductor, this is one bending here, and here another bend is there. If you are moving towards that bend, what happens? Again, that straight line becomes curved line. This is also not half, it is complete, like this. It will come until here, right? So it will bend, bend, bend. Now what is happening? The diameter, circumference, radius, it is decreasing. If you are moving away from the conductor, that circumference, diameter, and radius increased. If you are moving towards the conductor, it will decrease. It will decrease, 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 and at last it becomes again concentric circles, and that circle will become small, right? And okay, now what about the direction? We'll try to understand. Let me erase. Now, how to represent direction? That is a concept. It is quite simple. First of all, if we want to represent direction of magnetic field, we should have some idea regarding direction of current. Now, if you clearly observe this diagram, they have given two arrow marks. Here one arrow mark. Here, they have given one arrow mark like this. And they have mentioned like this. And here there is another line where they have mentioned like this. Guys, the point where current is entering, that point or the terminal is nothing but positive terminal. Blind mark. The point or the terminal where current is moving, that is positive. And the point where the terminal from which current is coming out, it is obviously negative. Guys, you have to remember one thing. You see, negative is the word starting with N. Negative word is starting with N. So N, you can match, it is north. So simply to say, here we have negative, na? So this side it will be north. Here this is positive, na? Whenever there is positive, this end you can observe, it becomes south. And we know what is the direction of magnetic field, always from north to south, isn't it? You see, it is from north, it is moving towards south. So arrow marks will be like this, towards south. So middle, inside the bar magnet, middle of the bar magnet, it will be straight line, isn't it? So from south to north. So that only we have arrow mark like this. Again, here we have arrow mark from north, and it is moving towards south. Arrow marks must be like this. So like that we can mention direction of current as well as direction of magnetic field around circular loop. So that's it in this lecture. In next lecture, we'll see remaining topics. We'll try to complete this chapter within 3 lectures.